We're ready now to move on to a new section of this chapter. We're going to start talking about quadratic functions. Quadratic functions are polynomial functions of degree 2, and this material is covered in section 5.1 of the textbook, so we're going back to this section now, 5.1. You should be pretty familiar with quadratic functions. This is really prerequisite material for the course. So the basics of graphing, I'm going to assume you're familiar with, but we are going to cover some applications. The applications are going to be fairly challenging, and I'm pretty sure this will be new material for you. So the applications we'll do at the end. All right, let's get started here. A quadratic function is any function that can be written in the form f of x equals ax squared plus bx plus c, where a, b, and c are real numbers and a is not equal to 0. It's kind of surprising that every quadratic function can be thought of as a transformation of f of x equals x squared, which means that implies that every quadratic function has a graph that's a parabola shape, very similar to the graph of f of x equals x squared. So let's look at an example here. We're going to consider f of x equals 2x squared minus 12x plus 3. And we're actually going to look at how this quadratic function can be thought of as a transformation of the x squared function. So I'm going to recopy it here. And I'm going to manipulate the formula for the function so that we can see the actual transformation. So let's move this up a bit. I'm going to get started here by factoring out a common factor at 2 from these first two terms of the function expression. So I'm going to have 2 times x squared minus 6x in parentheses plus 3. And then I'm going to take that coefficient of x inside parentheses, that negative 6. I'm going to divide it by 2 and square what I get. Negative 6 divided by 2 is negative 3. Negative 3 squared is 9. I'm going to add 9 inside parentheses. This is a process called completing the square. And I assume most of you have probably done this before. Now, I added 9 inside parentheses, and I've really changed the formula by doing that. So I have to compensate outside parentheses so that I maintain an equivalent formula here. So I still have plus 3. But now, really what I've done is I haven't just added 9 to this formula because of the 2 in front of parentheses. The effect of writing plus 9 inside parentheses is to add 2 times 9 to the whole formula. So to compensate, I have to subtract 2 times 9. So I have 2 times x squared minus 6x plus 9 plus 3 minus 18. The whole point of adding that 9 was to get a trinomial in parentheses that I could factor, and factor in a special way. It factors as x minus 3, x minus 3. It factors with both factors being the same. On the end, 3 minus 18 is minus 15. And we want both factors the same because then we can write this as 2 times x minus 3 squared minus 15. That's really the end of the completing the square process. This is now the form we were trying to get at. This is something the textbook calls standard form. And I don't really like this name so much because I kind of think of our original form as the standard form, I don't think this is standard language. But I'm going to stick with this language because it's in the textbook. And we're not going to work too much with standard form. I'll show you the little bit that we're going to do with it. But see, we can now interpret the function that we have here, the expression we have here, as a transformation of the x squared graph. And we're going to do that on the next page. So over here, what I did was notice I recopied what we just obtained. So we got to this point on the previous page. And I also wrote down the form we started out with. Our original function looked like this, 2x squared minus 12x plus 3. These are equivalent, and you can use either form, and you can go back and forth between them depending on what you want to do. Again, I think the 2x squared minus 12x plus 3 is going to be more useful to us in the end. But it's worth talking just a moment about why this standard form is a transformation of y equals x squared. So our first toolkit quadratic function whose graph is a parabola. So we can interpret this form we just obtained as a transformation in 3 parts. The 2 times is a vertical stretch by a factor of 2. The x minus 3 in parentheses is a horizontal shift 3 units to the right. And the minus 15 means we shift vertically downward by 15 units. Now, this initial point here is a point we call the vertex of the parabola, right? That turnaround point. And when we apply these transformations to the vertex, well, the vertical stretch doesn't move it. But the horizontal the horizontal shift is going to shift it 3 units to the right. And the vertical shift is going to shift the vertex down 3 units. So the vertex is going to move 3 to the right, down 15 units. Notice I set up different scales on the horizontal and vertical axis. So for the quadratic function we're working with, the vertex is at 3, negative 15. And so one advantage of this so-called standard form is you can easily see the 3 and the 15 there, 3 and the negative 15, the coordinates of the vertex. Now, I want to graph this whole thing. So I kind of know that the graph is going to be U-shaped. What I want to do is plot the intercepts. And to do that, I'm going to go back to the original form we had. I'm going to use f of x equals 2x squared minus 12x plus 3. So I'm not going to rely on that standard transformation. I could, but it's a little bit easier here to find the intercepts from this form. So since we have it, let's go ahead and do it. The y-intercept is when x is equal to 0. F of 0 for this function is 3. So 0, 3 is a point on the graph. And I just marked it there because my scale counts by 3's on the y-axis. And to find the x-intercepts, I have to set f of x equal to 0 and solve for x, right? It's like setting y equal to 0. And again, I'm going to take my function expression and set f of x equal to 0. And solve. And I have a little quadratic equation to solve. You can think about trying to factor this. It would have to be 2x and x. Both signs would have to be minus. Either 1 and 3 or 3 and 1. But you're not going to be able to get that minus 12x middle term. This is actually not factorable. So I would have to use the quadratic formula. And so let's go ahead and do that. X is equal to negative b, so that's actually minus a negative 12, because b is negative 12, plus or minus radical b squared is negative 12 squared, minus 4 times a is 2 times c is 3, all over 2a, 2 times 2. So x is equal to positive 12 plus or minus positive 144 minus 24 all over 4. X equals 12 plus or minus the square root of 120 over 4. So a lot of square root simplifying going on here. Let's come up to the right. 120, I think I can write that as 4 times 30, and 4 is a perfect square. So the square root of 120 is the same as the square root of 4 times 30, or 2 times the square root of 30. And 30 is 2 times 3 times 5. It has no squares inside. So we can't do any better than that, simplifying that radical. We got 12 plus or minus 4 radical 30 over 4. And now I can't cancel out those 4's, right? A little bit of basic algebra. I'm sorry, that's 2. That's my mistake. 12 plus or minus 2 radical 30 over 4. So again, I can't cancel this 2 with this 4. I can only cancel if I can factor out a common factor, and I can of 2 times 6 plus or minus radical 30 over 4. Now I can cancel. And I get x is equal to 6 plus or minus radical 30 over 2. So there are two possible x values here. 6 plus radical 30 over 2, 6 minus radical 30 over 2. And those are really my two x-intercepts. And you want to, for graphing purposes, you want to be able to get a decimal approximation for those. 6 plus radical 30 over 2. On my calculator, I get about 5.74. And for 6 minus radical 30 over 2, I get about 0.26. So I'm going to go ahead and plot the x-intercept points on my graph up above. So 0.26 on this scale, that's pretty close to the y-axis right here. Just approximating. 5.74 is pretty close to 6. And I have enough points now to be able to draw a graph with the intercepts. And I want to label these guys just for the record. So that x-intercept is actually 6 plus radical 30 over 2 comma 0. Of course, we used a decimal to help us. And this one was 6 minus radical 30 over 2 comma 0. And of course, our y-intercept point is 0, 3. Okay, and just one more thing. I think we're just about done talking about this example. Something about the symmetry of a parabola. I'm just going to draw a dotted line up from the vertex. There's a certain bilateral symmetry to a graph of a quadratic function. It's not around the y or x axis. It's around this vertical line through the vertex. And if you notice, for instance, the x-intercepts are equidistant from this vertical line. Like if I go 1, 2, and a little bit more to the right, if I go back 1, 2, and a little bit more, I hit the other x-intercept. They're equally spaced. Same thing with actually the y-intercept, the point 0, 3. From that vertical line, it's 1, 2, 3 spaces to the left. So if I go 1, 2, 3 spaces, this point must be a point on the parabola. That's actually the point 6, 3. So same y-coordinate as the y-intercept, but it's 3 units to the right of this, what we call the line of symmetry. So you can actually kind of, it's not really cheating, but you can get extra points. You can use symmetry to take the y-intercept point to get a free point here. You can plug in x equals 6 and see that y will come out to be 3 for this parabola. So again, we're not normally going to work with that standard form here. And we're going to go through one example where I'll show you exactly what I want you to know. But there's a nice, this was a nice example where we got a pretty parabola. The x-intercepts were a little bit messy to find using the quadratic formula. And we're going to continue in the next video segment.